Lecture 6, thank you for sticking with me to Lecture 6 of using astroparticles, particles from space to understand our world. Today the topic is going to be the isotopes and nuclei of cosmic rays and how they help us understand our Milky Way galaxy. So last week, just as a little overview if you weren't there, but reminder if you were, we discussed cosmic rays as damaging radiation. We discussed how maybe they're accelerated by supernova remnants, like the top left-hand figure there. We talked about the Milky Way as a whole having different kind of sites of accelerating cosmic rays, and that some of those cosmic rays, since we sit inside the Milky Way, at Earth, we measure those as interactions in the atmosphere, and so if we go to space, we're exposed to more of that radiation, right? And some of that radiation makes it to the surface of the Earth, but as a lower energy and different kind of particle at the surface. But in space, these are the cosmic ray nuclei that we talked about. And we talked about how it impacts life, including what we need to do to shield against it. And I told you that, actually back in Lecture 1, I told you cosmic rays are positively charged particles. I told you they were protons. And last week I told you that they're not just protons, so somehow I tricked you, right? But basically 90% of cosmic radiation in space is protons, just the positive charged nucleus of hydrogen atoms. And the plot on the right there shows you, see if I can get the pointer, yeah, the plot on the right there I showed you last week was the flux versus energy of those particles, and hydrogen H here, sitting way above all these other different kinds of elemental nuclei, such as iron. So the other 10% is all these other different kinds of cosmic ray nuclei, and that's going to be the focus of today. If you want a little reminder here, protons, positive charges, helium nuclei, 2 positive charges, and then we have different amounts of protons and neutrons together in the nucleus that give you even heavier elements like iron nuclei. And last week, we talked about how more charge, such as helium, has twice as much charge as protons, more damaging radiation, right? But I want to go back to the discovery of cosmic radiation that we talked about in Lecture 1 to ground you and give you the foundation of how we learned that there's actually that 10%. Because it's part of the story of how we use them to understand the Milky Way. So we talked about Domenico Pancini, how he discovered cosmic radiation when he submerged different electroscopes in boxes and put them underneath lakes, and he said, look, this radiation is going away when I put it at deeper sea level. And we talked about Victor Hess, who actually received the Nobel Prize by ascending in a balloon with a detector to find out that this radiation was increasing as he went in high altitude, right? And we also talked about Compton traveling the world and finding out that there's positive charged radiation, not gamma rays. Yeah, this is the 6th lecture in a row. I did that on purpose. Thank you for pointing that out. I almost forgot for a second. That's ridiculous. So Arthur Compton and his colleagues went around the world to find out that cosmic rays were not just neutral particles, and they're not negative particles, they're mostly positive particles, right? And we established that cosmic rays are protons in Lecture 1 from this. And so we transitioned by building new detectors, which is a lot of what I do. So that's going to be the focus that I have today too, is we went from having electroscopes, which were spontaneously having this mystery of why are they just discharging, right? We went and had cloud chambers that helped us learn about cosmic rays, about how they produce ionization from those charged particles. And then we built sophisticated detectors that combine those with Geiger-Muller counters, right, where we had a camera take a flash when the cosmic ray was going through both counters that were on either side of the cloud chamber so that we could autonomously do this. We could measure higher energy particles. We could figure out what kind of ionization it was, right? And so the story, going back to the 1940s, that I want you to have in your mind now, is a new kind of detector called nuclear emulsions. And this is where cosmic rays leave behind a track, a microscopic track that is later developed into a film. And this is the kind of new detector, nuclear emulsions, that were put on balloons in the 1940s that led to the discovery of pions and kaons and many different, and basically was part of the birth of particle physics too. is a very important highlight here. So I talked about, I believe also in lecture 2, I highlighted that Cecil Powell's group in the UK was able to use these to discover pions. And these kinds of nuclear emulsions lead you to different tracks, different thickness of tracks, different kinds of decays happening. This was actually the famous pion decay track from one of these flights on a balloon. And this actually led us to understand that pions are charged particles too. And so I'll come back to pions in a little bit. But just a year later, 1947, pions are discovered. Just a year later, Phyllis Fryer here at the University of Minnesota nearby was a graduate student and decided to work on putting those nuclear emulsions herself on balloons. And she actually found evidence that there were high charged or heavy nuclei in those cosmic radiation, right? This was the first reported measurement of heavy nuclei, of cosmic rays that are not just protons, that are not charged pions produced in the atmosphere. This is the actual nuclei of heavy elements in cosmic rays. She even put it on balloons. She highlights that in her paper in 1948, High Altitude Flights and Free Balloons. Give evidence for the nuclei of atomic numbers of about 40. And this is confusing because what was being put together around the same time too, probably 20 years before, is how the elements fill our periodic table. We had just started to really understand that the periodic table can be organized into helium, hydrogen having 1 proton, helium having 2 protons, but maybe some neutrons. And we organize this as the chemistry that you're used to with the periodic table here, right? You have helium with high charge, and then you have even higher charge, and you can have really heavy elements that are metals. And so in cosmic rays, things that are heavy are anything above helium, basically. In astronomy, anything above helium, really. It's heavy, right? And the important thing that you need to be reminded of now is each of these elements has a charge, the nucleus of them. When they're elements, they really have electrons. They're neutral. They're cold. They're at the temperature of us in the room. But their cosmic rays have so much energy that these are just the nucleus of those atoms. Their electrons have been ripped away. They're flying so fast through space, been ripped away. And so you can have protons and neutrons together forming a nucleus. And the number of protons, decides the charge of that nucleus, decides the element. That's what we call hydrogen in cosmic rays, is just protons. Sometimes there's a neutron too. That's called deuterium, right? That's a type of isotope. But we can even have much heavier nuclei in cosmic rays. We can have protons like chlorine that have 17 protons, but different isotopes of them, some that have 20 neutrons and 18 neutrons instead. So the charge is the same, but the mass is completely different between these two particles. And what we'll talk about later in the lecture is that some combinations of these isotopes, these different elements, are unstable. Those nuclei are unstable and they decay. And actually neutrons do too. Free neutrons decay as well. So we don't really measure those in the cosmic ray spectrum because they don't make it to Earth if they are born somewhere. But different nuclei decay, and that's the reminder that we needed. And so in 1948, it's actually a very interesting time in astrophysics because there were debates about the origin of all these elements. There was this birth of quantum mechanics, the ability to do nuclear fission, the understanding of different kinds of radiation, the discovery of all these particles, these high-charged nuclei colliding in the atmosphere. Now we have heavy nuclei of cosmic rays, and at the same time, the same year, in fact, George Gamow publishes his famous Big Bang Theory paper. So this is really the start of the idea that everything in the universe was actually one kind of singularity which expanded and cooled and produced everything else afterwards that we are part of today, right? So this is the paper on the right here, shows you, I believe Gamow was only added to the author list to make it alpha, beta, gamma, but I think that's just a rumor. Before it was just alpha and beta maybe, but I really think it was probably the inverse. Gamow was like, I'll do all the work, and everybody else said, well, alpha, beta, gamma sounds good. But the idea that I want to get across to you here is that in the origin of the chemical elements with the Big Bang Theory, protons and neutrons synthesize. They're all mixed together, and out pops helium, out pops lithium, out pops boron, out pops beryllium. And this is the kind of study that needed to happen to say, is George right? So the best way to go find out if George is right is to go ask your geochemist friend that you obviously all have named Victor Goldschmidt. He just happens to have access to all these meteorite samples, and he says, well, I have an idea. I can measure in these meteorite samples from the universe, how much of each of those kinds of elements exist. And so that's the plot on the right. This is inside of the paper of the origin of the chemical elements. And you can see the solid line shows what George Gamow thinks is the Big Bang Theory. And he does not bad. I mean, you get a lot of abundance here. These are logarithms, so this is like 10 to the power 8 and 10 to the power 0. And this x-axis is the atomic weight. So hydrogen and helium are down here at 1, basically. And then carbon, nitrogen, oxygen, all the way over here at 6 and 8 and 10. But these are the heavy elements. And so from those samples of the meteorite, you can see George Gamow is completely wrong about one thing, very specifically. These light elements here, George says they should be up there. And they're way down here. He's a factor of 100 million off from what is measured in the meteorite samples. So the Big Bang Theory is not correct. No, I'm just joking. It's that it's actually famously called at the time the mass gap problem. Basically, there's some unstable nuclei, there's lithium-5 and beryllium-8, that can't be made and stick around. But George needs to account for this in his theory, right? So this is the question. How do you deal with the mass gap? How do you make the kinds of nuclei that George is saying we should have here? Most of it is hydrogen and helium. But all these other nuclei need to be made somewhere. And so we come back to Phyllis Fryer in the same year. He says, well, George, I just actually saw lithium, so he can't be completely right. But really, the high-energy process that makes these cosmic rays that Phyllis just measured, then, the question becomes, is it making all of the heavy elements as well? Right? So there's some mechanism that started to tickle at the scientists, and the curiosity started of, how do these elements get distributed in the universe? How do they get made? How do they get distributed? How do we get cosmic rays with heavy nuclei? All of this birthed around 1948. And one of those follow-up studies showed a carbon, nitrogen, or oxygen nucleus track, because in these nuclear emulsions, it was harder to tell the difference between those kinds of charges. She illustrates the point here of different kind of investigations were underway to figure out how do we link all these things together. And so, as early as, I think, 1920 with Eddington, but later in the 1930s with Hans Bethe, we started to understand that at the very least, there's proton nuclear fusion in the sun, right? That there's a way to produce helium that's not just a part of the Big Bang. There's a way to produce it that comes from the sun's core, right? This stellar nuclear fusion of protons in the sun that is hot enough to make helium. And so you can see the kinds of reactions here with little byproducts of neutrinos and even positrons as well. And so Hans Bethe in the 30s said, I think maybe the late 30s, this is what powers the sun. But the immediate barrier here to solving George Gamow's mass gap problem becomes, what about helium fusion then? Right? Is there a way for the heliums to fuse and give you other nuclei? And the answer is, well, not really, because beryllium-8, if you took 2 helium-4s, which is what comes out of this proton-proton chain that's successful at describing what's happening inside the sun, if you take these 2 helium-4s that must be then inside the sun, you wouldn't be able to get a beryllium-8 because beryllium-8 is unstable. They knew that at the time. It decays actually with a half-life of what's called an 81.9 attoseconds. The unit is attoseconds. So if you're not used to that unit, I'll give you a little way of thinking about it. Speed of light can travel 3 hydrogen atoms in 1 attosecond. So that's how unstable this nucleus is, right? Beryllium-8, unstable, non-starter. How do you can fuse proton all you want, you get helium all you want. You can't explain the mass gap with this kind of nuclear fusion. And so then the question actually started to be, well, maybe cosmic rays are just born out of the primordial soup. Maybe they're coming out of the Big Bang. Maybe George is right, and there's some other way for us to deal with the mass gap, but these heavy nuclei of cosmic rays, maybe that's where they're born. And primordial means from the Big Bang. Everything after that, the stuff that's fused in stars that I just talked about with the helium, that would not be primordial, right? That's from stellar nuclear fusion. So saltpeter and Hoyle come along and say, I have a solution of how we can get that mass gap problem fixed in a way. It doesn't really fix the problem, but it kind of does. It's called the triple alpha process. Remember those two helium-4s? Let's add a third one. Let's do it fast enough that allows 4 heliums to produce a carbon-12, jumping the beryllium-8 problem before it decays. Fast enough density, hot enough material to produce carbon-12. And that actually led also to different kinds of fusion ideas, and this is something that started to develop very thoroughly in the 1950s was stellar nucleosynthesis as a way to create the elements, as a way for us to explain that maybe everything really started as hydrogen and helium, and things above that are made in the cores of stars. So the CNO cycle is one of those other processes that's slightly more complicated because you have a bunch of nitrogen and protons fusing to make carbon, which hits another proton, which makes more nitrogen, but a different isotope. And so this kind of cycle is one of those things that was proposed. And finally, there was evidence in 2020 by Borexino, the instrument that detected the neutrinos coming from the CNO cycle in stars. So we know the CNO cycle is producing these kinds of elements as well. So we know heavier elements than hydrogen and helium are produced inside of stars. So we can come back to the origin of these chemical elements and provide a little summary. We say stellar nucleosynthesis, and I'm summarizing an entire research field here, by the way, but stellar nucleosynthesis is where you have stars that start off with the protons from the Big Bang, but fuse and make helium, and later in their lives they fuse helium and make more material, and the more fusion that happens, the higher the nuclear content becomes of protons and neutrons, and eventually you get to this iron core. Right? And so this is the kind of summary that we have of what the origin of the chemical elements is. So the heavier elements are not from the Big Bang. They're actually from stellar nucleosynthesis. And then the question is, what about those heavy nuclei in cosmic rays? Are cosmic rays coming from this stellar nucleosynthesis? And so if you go back to George's plot and you say these meteorite samples, and you look at George's prediction, we have a slightly updated plot in the 1970s where we have the abundance from those meteorite samples as this dashed line. So the x-axis here is the atomic number. The y-axis is that relative abundance again, but with this logarithm scale very clear, right? And you can see the dashed line shows you at the light elements of lithium, beryllium, and boron, you have that compared to cosmic rays in this thicker dashed line. And so if you go measure those heavy nuclei that Fryer discovered in cosmic rays, there's this huge issue where it's what's called overabundant in these light elements of lithium, beryllium, and boron. Okay? And so something is happening with cosmic rays that is not reflective of what happens with the rest of the universe, right? With the stellar nucleosynthesis of the elements, you get this curve, this dashed line. With cosmic rays, you get this one. Why is it overabundant here? And there's actually a lot of overabundance here as well. So stars are not making this lithium, beryllium, and boron. They can't, right? But we do observe that lithium, we do observe that boron, we do observe the beryllium in the cosmic ray spectrum, cosmic ray measurements of the mass and the nuclei. So some scientists thought in the 30s that maybe cosmic rays are just born in the stellar nucleosynthesis of stars, but the energy scale didn't match in the 40s, and so they started to rule this out. The energy scale of that stellar nucleosynthesis is mega electron volts, but the cosmic rays are giga electron volt. That's a factor of 1,000 more energy that doesn't seem to happen in stellar nucleosynthesis, in the cores of stars, right? And so one of the papers here shows you from Fryer that this is, or maybe this is one of her colleagues, the measurement of 1 in 15 BeV. So this is when they still use the unit in America of billions of electron volts instead of giga electron volts. That was, so they had to change that. I remember trying to explain this once, and maybe I did a bad job. So they had to change the unit, right? Because giga electron volts is what we use now. Giga of anything. Gigabytes, SI unit for a billion. But the British used a B as well, but that was actually not a billion. That was a British billion, which is actually a trillion. So they had to change the B here to not confuse the British, right? So they changed it to giga, and then the British ended up changing it anyway from their trillions of Bs back to giga as well. So everyone kind of coalesced into the gigavolts, the giga electron volts. And at the same time comes along Bodden-Zwicky, basically 1934. They propose that these stars can't sustain this fusion forever. There's probably some kind of explosion that occurs, and their famous theory was proposed in 1934, so you've probably heard of that one. And so last week I kind of summarized this as supernovae are the explosions of stars, and their remnants have enough energy to accelerate cosmic rays around them. So on the left is the animation of what a supernova explosion of a star looks like. So the stars that start here are producing helium and heavier elements from stellar nucleosynthesis, but eventually an exotic event of an explosion of that star occurs. But the resulting remnant, we think, is capable of producing and accelerating cosmic rays, the material around it, to extremely high energies. And where this explosion comes from is sort of intertwined with our story of cosmic rays, so I have to spend some time on it too. The plot I'm showing you here is the y-axis is the binding energy of the nucleus, and the x-axis is the number of nucleons in that nucleus. That's a proton or a neutron, okay, just total number. So a carbon-12 would have 12 nucleons, right? And you can see highlighted here, protons, hydrogen-1, helium-3, you even have hydrogen-3, which is tritium, and then you have helium-4 up here, and you can see this motion of how the binding energy increases, right, as the number of nucleons increases, until you get to iron-56. So if you add more nucleons, you get more stable nuclei until this guy. Then it doesn't happen anymore. You're not going to be able to make these guys, just like you didn't make lithium-6 and 7. It's not energetically favorable. So the accumulation, what happens in a supernova remnant is the accumulation of fusing different material until you get to here, and then there's nothing past that goes upward. So you can't fuse anything more. And so there's an increased pressure because now you have all this material here that can't release energy. It just keeps, gravitational collapse occurs, it just keeps getting hotter and smaller, and eventually results in the kind of explosion that we saw on the previous slide. And this is an active area of research too. The way I think about it, and I've tried to explain it to my wife, is it's like feeding your kid donuts. The donuts are the protons or the nucleons. They want 56 of them for some reason, right? But then eventually they don't want another one, right? That's exactly what happens with a supernova. All right, they explode. So cosmic rays, the summary of this is cosmic rays are accelerated in the Milky Way from sites probably like supernova remnants. And so I showed you this animation again last week, but I'm going to show it again. You have a zoom in inside the center of the Milky Way or some region of the Milky Way where eventually a supernova goes off. But after that explosion, there's still this expanding material, this acceleration of material around it, right? And this is what we call injection of cosmic rays. But those happen in bursts over the age of the Milky Way, and they can stick around. The supernovas last for much longer than the explosions do. And so this is why I was telling you that cosmic rays fill the Milky Way like a sea, right? The solar system is immersed in this sea of cosmic rays because these supernovae go off in different, maybe 2 or 3 a century, but over millions or billions of years, right? That's a lot of bursts. That's a lot of supernovas. That's a lot of acceleration. That's a lot of nuclei produced in cosmic rays. And you can't use the cosmic ray direction to find out where they came from. It's not so simple. The reason it's not simple, but they hoped it would be at the time, actually, in the 48 and 50, when they found out these were heavy nuclei, they said, well, let's just find out where they're coming from. It turns out they're isotropic. That means they're coming from all directions. You can measure the direction of your cosmic ray, even on your balloon, but if you measure a lot of them and you point back and you make a map which direction they're all coming from, it's uniform everywhere. There's no clear, they're all coming from that direction, right? And Fermi had a solution to this, actually, in about 1950. He said, there's galactic magnetic fields. And before that time, it might have been an area of attempt at research, but I don't think it was ever, as far as I can tell, it wasn't ever really thoroughly investigated as a means for particle physics or for cosmic rays until Fermi had talked about it more. As the galactic magnetic fields, after he proposed the solution, basically, even if you had all these remnants accelerating cosmic rays, those cosmic ray nuclei are charged particles. And the entire Milky Way has a chaos mess of magnetic fields. It's not just one direction. It's not a magnetic field that goes in one direction. It's a mess of magnetic fields. And those magnetic fields deflect the particles. Those charged particles, they deflect charged particles, right? And so the order of magnitude here that was determined in about the 50s and 60s was that the amount of the magnetic field, the strength of it, is about 1/3 of a Gauss. So that's 100,000 times, almost 1,000,000 times weaker than your fridge magnet. But because the Milky Way is so vast, it deflects these cosmic rays on a large enough distance scale, but the Milky Way is so fast that you can't point these cosmic rays back to their sources. So the diagram you can have in your mind is your supernova remnant goes off, you get a proton cosmic ray, and it kind of just deflects off of the magnetic fields. And if you measure it on Earth, it's pointing back somewhere else, right? You also have gamma rays and from things like pions and stuff that I'll come back to. But this also means that cosmic rays are basically confined to the Milky Way. They can't really escape. They can kind of leak out of the edges, and this is what people in the 70s thought started coming up with this model of cosmic rays in the Milky Way called the leaky box model. But most of the time, they're confined. They can't travel directly out of the Milky Way. They keep deflecting on these magnetic fields. They're confined to the extent of the Milky Way, unless they have enough energy. And just to compare it for you here, if you had a PeV, a peta-electron volt cosmic ray, which is 1,000,000 times that giga-electron volt scale, its gyro radius is 1 light year. And so what does that mean? That means that if you think of it like this, you have a magnetic field going this way, your cosmic ray charged particle nuclei is an ion, and it's going to deflect, it's going to bend in this like circular pattern with a radius of about a light year. But the Milky Way itself is 20,000 light years across, and probably at least 5 to 10,000 light years thick. So, cosmic rays are basically confined to the Milky Way. To give you a little bit of an animation to describe all that better, you have a supernova remnant accelerating cosmic rays, which travel in these weird zigzaggy lines, and then they eventually get measured here on Earth. And those supernova remnants also emit gamma rays. And so we can use gamma ray measurements to say where those supernova remnants are, but those travel in straight lines. They're neutral particles, so that's what this purple is showing you, right? That those are neutral particles. And so let's come back to those gamma rays. Oh, actually, I had one thing to say about this. This one. Why is it doing that? Sorry. So I was thinking about this for some reason the other day, but the best way to think about this is something I talked about with my dad. When I go for a drive, when I need to travel somewhere, I'm like a gamma ray. I go directly where I need to go. My dad, for some reason, decides, I kind of like to take this way or that way, and I like to see the sights and stuff. We're completely different people in that regard, but the first thing I thought of was this difference, right? Anyway, so now, like gamma rays, if you look at the sky, the Milky Way, in optical, you get this picture, but when you look at it in gamma rays, remember, if you put on your gamma ray lens, you get a bunch of different structure, right? Because you can look at the things that trace these high energy particles. These are tracers of the high energy particles. And so if we come back to that overabundance in cosmic rays of light elements, the picture we have in our minds is that the supernova remnant accelerates cosmic rays, which are these kinds of materials, mostly protons, but also the kinds of materials that were fused in the cores of stars, the kind of material that was left around. And eventually, as they travel through the Milky Way, they can collide with the interstellar medium. The interstellar medium is a bunch of protons. Sometimes there's molecular clouds, but basically there's other high-energy collisions of those cosmic rays. We're not measuring all the time. We're not measuring cosmic rays only here. We're measuring them after they've collided, right? The kind of collision you can have here is what we call primary cosmic rays, the ones that came from the sources, colliding with the interstellar and producing different kinds of nuclei. They take a heavy nuclei and break it apart into two smaller ones. Okay? And this actually explains the overabundance really well. It says that in cosmic rays, you take all of these heavy things, and as they propagate in the Milky Way, they give rise to, more often than not, these guys that couldn't be made in the cores of stars. They're only made in what's called the spallation of cosmic rays. So the primary cosmic rays are accelerated with a sample of this stellar material, different kinds of nuclei. For example, your carbon-12. Carbon-12 is made in the cores of stars. Carbon-12 has 6 protons and 6 neutrons. If it collides with an interstellar medium proton, or maybe a molecular cloud such as helium or something like that, it rips apart the nucleus of your carbon here and results in a different kind of nucleus, like beryllium. And this produces what we call secondaries. So we now have this distinction of primary cosmic rays and secondary cosmic rays. So in this example, you had 6 protons and 6 neutrons, carbon-12, and you got 4 protons out, so that's beryllium, and you still had 6 neutrons, that's called beryllium-10. But the other thing you get out is this black box that I'll talk about later, and gamma rays. So those gamma rays are not just coming from supernova remnants, they're also coming from the actual interactions of cosmic rays propagating and colliding in the Milky Way, right? And this is very similar. I want you to think about it this way too. It's very similar to the collisions that we talked about with cosmic rays in our atmosphere. As soon as a high-energy cosmic ray particle hits a molecule in the atmosphere, just like a molecular cloud, just like the interstellar medium gas, it breaks apart. Right? That's why we have to go to space to measure those cosmic rays. And so you get a mess, we said you get a zoo of particles at the surface, and some of those particles are pions, and some of those particles are gamma rays, right? And so if we go back to our gamma ray sky and we look at what we see, we can talk about the sources, such as this one, Cygnus X. We can talk about high energy sources, because gamma rays are signatures of those cosmic ray nuclei and protons colliding with other material. But we also see the disk of the Milky Way in gamma rays, right? You can see that clearly here. And this disk structure, this is a glow in gamma rays because there's a bunch of cosmic rays interacting, right, through that propagation, that messy random walk, the way my dad drives kind of thing, through the Milky Way, right? And then last, what you notice about the gamma ray sky that I do want to highlight and point out now is there's a bunch of gamma ray sources above and below the Milky Way. And those are actually extragalactic sources that I'll talk about in the very last lecture of this series. So, going back to the idea that supernova remnants accelerate cosmic rays, what's an active area of research nowadays is that it's probably not just supernova remnants. They can't seem to give us cosmic rays that reach the energies, the PeV energies that we measure, or that we've detected above the atmosphere. Remember that PeV scale is 1 million giga-electron volts. That peta-electron volt scale is 1 million times more energetic. And so there actually might be other sources in the Milky Way. And so if you look at this plot on the right, you have the flux and y-axis, the energy of the cosmic rays on the x-axis, and you see the sun here can produce maybe lower energy particles, right? Lower energy cosmic rays, but the giga-electron volt scale here is 10 to the 9, right? So it's it's a third of the way through here. But in the galaxy, we know that cosmic rays can be accelerated all the way out to here. And then there's a break, there's a change in behavior of this flux with respect to energy. So at the low end, you have change in behavior. At the high end, you have change in behavior. And if you go look at the data directly, you see another interesting thing. It actually changes with the different kind of cosmic ray nucleus you're looking at, right? So what we're showing here is the flux on that y-axis again, maybe some weird units, but you can just trust me on that. And you have proton cosmic rays, helium, carbon, nitrogen, oxygen, magnesium, silicon, iron. And I could sing that again if you wanted me to, but I'm not going to, right? But you can see all the different measurements we have from these different experiments pointing out to us that these different cosmic ray nuclei have a different flux energy dependence. At low energies, I've drawn a vertical dashed line here, you see that iron, this change in behavior happens at a higher energy than proton, which happens over here, right? This is evidence of solar modulation depending on the actual charge of the nucleus and maybe even the number of neutrons in the nucleus. And at the higher energies, I've drawn another vertical dashed line, you can see that behavior extending further for iron versus protons, right, and in between. And this is evidence that there's a high energy limit in our galaxy to producing protons, but an even higher limit for iron, right? And so this is what we think, that there's galactic accelerators that are different from extragalactic. And some of the other kinds of interesting high-energy astrophysical objects in the Milky Way we think accelerate cosmic rays. One of those is the center of the Milky Way, which is a supermassive black hole that's 4 million suns, mass of 4 million suns. We also think that there's these fancy areas in the Milky Way called stellar clusters. And inside of some of those stellar clusters, there's one kind of astrophysical object I want to highlight called a Wolf-Rayet star. And Wolf-Rayet stars have very strong winds. They do all the fusion, the stellar nucleosynthesis that I talked about, and they produce heavy elements in the center with this like profile, lighter on the outside or whatever, and then heavier on the inside. But basically they shed the outer layers in a huge amount of mass loss that happens, on the order of tens of thousands of years, but it produces a huge wind, kind of like the sun. The sun has this solar wind that we talked about, but this is to an extreme extent. This mass loss of the outer shells means that the material that's being produced is higher and heavier, higher charged nuclei, right? Heavier nuclei. And so one of those, Wolf-Rayet stars is actually very interesting in terms of isotopes of cosmic rays. For example, neon-22. And so the animation down here shows you a Wolf-Rayet star animation shedding its outer shell in this mass loss of stellar wind, right? It can reach up to 3,000 kilometers per second, apparently, in these stellar winds. It's magnificent. And what we did is went and measured the abundance of cosmic ray isotopes, for example, neon, 22, 20, and 21. And so the plot on the right here shows the measured abundance versus energy, and neon 22 versus 20. The ratio of those things is what's going to be used a lot throughout the rest of the talk. But basically, you have a production of neon 20 somewhere, probably made in the core of the star and then accelerated in cosmic rays, right, the stellar wind. And then you have neon 22, maybe the same thing. But if you go and compare that ratio, that neon 22, and you compare it to what we see in meteorites, there's this same overabundance. There's much more neon-22, right? Before I said there was much more lithium, beryllium, and boron in cosmic rays. Here there's actually just more neon-22. Not 20, 22 only, right? And that's a curiosity because in all of these other measurements of this ratio, neon-22 and 20, right, for things like these meteorites from our geochemist friends, it's a much lower fraction. And so this is evidence in an active area of research that maybe this is evidence for Wolf-Rayet stars, those stellar winds producing and accelerating cosmic rays. But we also can get heavier elements than iron in cosmic rays, right? And to produce those heavier elements, not in cosmic rays, just in general, you have to go past that iron 56 nucleus, right? And so what we think is possible with supernovae is that when they explode, they can give you elements, they can fuse and make elements that are higher than charge of about 34, right? So you see on the plot on the right here, is the number of neutrons on the, sort of like the arrow on the x-axis, and number of protons. So as you go up a diagonal line here, you would be adding one proton, one neutron, one proton, one neutron. And this is divided into little sections. You can see the fusion, the stellar nucleosynthesis of iron here, and this red line only gets you up to iron is a charge of 26 here, right? Supernova, we think, get you to a charge of 34, and maybe up to 10, which is about 50. But you and I, we know that there's much heavier elements. There's gold, platinum, and lead with charge, with number of protons in the nucleus of 78, 79, 80, right? So where did those come from? Supernovae, our current understanding is that maybe some supernovae can produce them, but not enough to show us the abundance we see. And not until probably, the past 10 years have we found another candidate, really, that has a lot of evidence to suggest maybe there's another way to make heavier elements than supernovae. Traditionally, 30 years ago, it was sort of a no question. Supernovae make everything heavier than helium, right? Everything heavier than iron. But nowadays, we think that there's something else. We think there's neutron star mergers. Okay, and these are called kilonovae, and was actually one of the first detections of a neutron star merger was with gravitational waves in 2017. But basically, in a neutron star merger, neutron stars are made of neutrons. And so they're enriched in neutrons, and so you can get much heavier nuclei because you have so many neutrons sitting around already. Something that supernovae seem to fail with. They don't have enough neutron content to produce those. And so if you look at this plot, you say supernovae sort of give us the elements down here. Neutron star mergers are a very good candidate to get us all these other heavier elements. So what does this have to do with cosmic rays? So there was a few flights of this experiment called the Trans-Iron Galactic Element Recorder, or TIGER. And there was 3 of those flights in the late 90s, early 2000s on balloons. And then there were 2 follow-up flights a decade later, 2012 and 19, of a detector that basically wanted to go measure the abundance of these very heavy charged nuclei, right? Wanted to see in cosmic rays, is there gold, is there lead, is there platinum? And the kind of data that existed at the time is sort of absent, still sort of is absent here, right? You have the charge of 78, you have maybe some data points here, but there's a lack of data out here, right? And so that's the point of this, is to say, well, if these neutron star mergers really fuse and make really heavy elements, we should probably see some of those in cosmic rays as well. And so now TIGER is a very successful cosmic ray instrument that's actually going to go on the International Space Station. So they have some significant improvements over the balloon ones. So this was the flight from McMurdo, from LDB, Long Duration Balloon Facility in Antarctica from 2019 of Super Tiger 2. But the reason they need to go to space is because space is better, right? It's not just better, it's because there's residual atmosphere above the balloon. The balloon only gets to 40-kilometer altitude, whereas the ISS is at least 3 or 4 times higher than that. Probably the altitude's closer to 200 kilometers or something, right? And so it's actually going to be installed in 2027 at the Columbus module here, attached to the International Space Station. So they're going to be operating until the ISS is decommissioned in 2032. So stay tuned for results from that, where we look for gold and platinum and lead in cosmic rays. But we already have some cosmic ray detectors in space. We have, from 1997, we have the ACE Explorer, the Advanced Composition Explorer, or ACE, which had a few cosmic ray detectors on board. And it actually reported, I still think it's taking data today, but in 2016, about 10 years ago, it actually published its first result of a very curious thing, which is iron 60. So remember, iron 56 is the iron that you can't fuse past that, but this detector measured iron 60. And iron 60 is a very interesting isotope of iron because it decays with a half-life of 2.5 million years. It's a very long-lived isotope. So for those of you who are curious, like carbon-14 carbon dating is about, I think, 20 or 30,000 years. This is 100 times longer, right? 2.6 million years. But the question is, how did that even get in cosmic rays in the first place? You don't get that from spallation. Spallation gets you lighter elements, right? Not heavier. And this by itself is very interesting, but then also Voyager, which we talked about last week a little bit, escaped the solar system, or went outside the solar system, and measured cosmic rays in the interstellar medium for the first time. It also reported an excess of iron compared to what we thought it should. And so the active research that we're talking about now, the kinds of things we're thinking about is this evidence for a very recent, within the past 2 to 3 million years, some kind of nearby supernova activity. It has to be nearby, and it has to be young. It has to be young because that iron 60 is still there in cosmic rays. And it has to be nearby because it's an excess over everything else, right? And there's many other cosmic ray detectors that we have actually in space. One of those I want to highlight is the Alpha Magnetic Spectrometer, which is on the International Space Station here. One of its spacewalk maintenance pictures is shown at the right there, which is pretty cool. But the one I really want to talk about is the Chicago egg. So those of you might know about the Chicago egg, but I'll try to give you a little bit of history that you don't know. So the Chicago egg was a cosmic ray detector that was, flown on this flight of the Challenger shuttle. So the egg itself is actually very large. It was the largest cosmic ray detector designed at the time in 1985. It was designed right here at the University of Chicago and launched, in 1985. Many different wonderful scientists here like Simon Sorty, Dietrich Muller, Peter Meyer, and even this name, Grunsfeld, which you might have heard of. So he turned out to be an astronaut, right? Just so happened he went on to be an astronaut. And but he helped was a main designer for this Chicago egg experiment. And then he later became an astronaut and actually did a lot of those, a few of the Hubble space telescope fixes as well. And actually another interesting story about this is this Challenger mission didn't reach the altitude it was supposed to. It had like 15 or 10, like a dozen scientific instruments on board, including this one, but it never got to the right altitude. And all of those scientific experiments were very upset about it, but this one was not, actually. This one was happier with the lower altitude because it didn't have the readout capability to handle all of the data from all of the cosmic rays if it had reached the real altitude. It would have had to operate on what's called a duty cycle. So one of the other instruments on this mission was some kind of beverage dispenser to see if they could basically give you Coca-Cola or Pepsi in space for astronauts, and it turned out not to work. It became very warm and frothy as soon as they used it, and they said, that's disgusting, so they transitioned to Tang after that. But anyway, so one of the main results besides those things about the Chicago Egg and Challenger mission was these ratios. I'm going to come back to ratios that I talked about before. So I've talked about primary cosmic rays and secondary cosmic rays. This is the secondary to primary ratios. So we talked about carbon being a primary and boron being a secondary, right? We said that the stellar nucleosynthesis that occurs can produce carbon. And so if cosmic rays are accelerated from supernova remnant sites, there's a lot of carbon, but not boron. But that carbon cosmic ray can collide with the interstellar medium, producing these lighter elements like boron. And so the Chicago egg actually went and said, well, this is a really interesting scientific measurement to perform, because if cosmic rays are confined to the galaxy or there's a lot of material in the galaxy, we should measure a lot more boron. There should be a lot more production of boron. So the boron to carbon ratio is an interesting thing to go measure, depending on how much material those cosmic rays, how many interactions have those cosmic rays gone through. And so this plot on the right shows you different model predictions for changing behavior of boron to carbon ratio, because in some models you get a lot more boron because you get a lot more interactions, and then in others you get less. And the measurements were very interesting. They show you that there's this steep fall off with no increase, and sort of has this profile to it. It even has a nice power law, what we call power law relationship here, where you have the boron dropping as a function of energy, right? And they even measured other ratios. You can see the carbon to oxygen ratio, both of those being primary, is basically flat, right? Not as much interesting features going on. And so this is a primary to secondary ratio, or secondary primary ratio that was interesting from the Chicago egg. So going into the 90s, the picture that we had was that a bunch of cosmic ray acceleration occurs across the Milky Way, and so supernova remnant sites across the Milky Way in this little diagram show you producing a lot of cosmic rays. They can't point back to their sources. There's magnetic fields. They sort of just diffuse or random walk around the Milky Way, and they undergo interactions. And nowadays we think maybe there's Wolf-Rayet stars, there's neutron star mergers, there's clusters of stars instead of just supernova remnants, but it's an active area of research. We think that those kinds of sources produce primary cosmic rays, right? And we think that their composition should reflect what they started with, right? They can't be accelerating boron at their sites because there was no boron to accelerate. But the spallation or propagation of primaries results in a bunch of secondaries. So you get the carbon primary hitting the interstellar medium while it's moving around or random, just going on a drive in the Milky Way, and eventually hits a proton and produces other kinds of elements, right? Such as those light isotopes. But I want to come back to the other things that must be happening from the spallation, the black box, right? So I told you there was a black box. We talked a little bit about gamma rays, right? But there's also muons and electrons and positrons, and there's even neutrinos, okay? But I'm not going to talk about neutrinos. I already did that. So instead I'm going to talk about not muons either. Muons decay. I think I talked about that in muon tomography lecture maybe, but just as a reminder, muons decay, they can't travel anywhere really in the range of the universe, right? In the range of the Milky Way galaxy either, right? They're too short-lived. They would be having to be travel such a high energy in order to have time dilation kick in to not decay away. They can only go hundreds of kilometers at the energies that they probably are produced in these spallation interactions. So then the question is, what about electrons and positrons? So after the Chicago egg, after Challenger of 1986, the tragic accident there, instead of putting another detector in space, the UChicago group went and designed the high-energy antimatter telescope, or HEAT. Right? And so this was a balloon-bore instead cosmic ray detector where they wanted to measure positrons and antiprotons, and it flew in 1994 to go make that measurement. They used a superconducting magnet because the best way to tell a positive and a negative charged particle apart is to bend them in a magnetic field to see which direction they go. There's other methods nowadays that are competitive as well, but at the time this is a very good idea. And the kind of diagram from their 1995 paper probably is a stack of detectors that utilizes the coincidence measurement, and the cosmic ray travels through the magnet, and the positive ones, the positrons, will deflect one way, and then electrons will deflect the other way. And they actually found a hint of an excess of positrons. And so this, at the time, was just a hint, because as a balloon mission, it's got atmosphere above it, and so it's not so clear if it's exactly an excess. It's not enough to say, weren't confident enough, but it definitely did not match what they were expecting. So these hints from the HEAT instrument led to other detectors in space, like PAMELA, which is the Payload for Antimatter-Matter Exploration and Light Nuclei Astrophysics. That one was launched in, launched in 2005 or 6 and operated for a decade, as well as AMS, which I mentioned with the spacewalk before. And so they went and measured those positrons, both of these instruments actually in space, and they found that excess to be real. So something in the Milky Way is producing more positrons than we expect, right? And this is a curiosity. This doesn't make a lot of sense to us because the boron to carbon ratio, we seem to be able to say looks kind of like it should change with energy, which produces some boron from carbon primaries, right? The propagation looks about right. What is producing this extra positron? What's making extra antimatter in the Milky Way? And a lot of people said, dark matter, and they still do, which makes sense. Usually, if you don't know what it is, you call it dark matter, right? So there's many theories of this, and the flux of those of the positrons on the y-axis here versus energy of the positron on the x-axis shows you one theory that can, kind of produce this excess of dark matter compared to what should be, what our understanding is of cosmic rays colliding with the interstellar medium, right? Something's not adding up, but maybe dark matter is the answer. The other really interesting candidate to explain this excess is pulsars, okay? So pulsars are these wonderful high-energy objects that undergo ridiculously precise and fast spins, and they produce from that spin, they produce ridiculously strong magnetic fields and a beam of radiation out like a jet almost, off the axis of the spin. And they're also known, because of those strong magnetic fields, to basically clear the surroundings of everything except for electrons and positrons. There should be, or sorry, I said that the inverse way. They should have an excess or a lot of extra electrons and positrons in the surrounding medium to accelerate because of those strong magnetic fields. And so this is also an active area of research is, can pulsars produce the positrons and explain that positron excess? And so this is one example of a simulation of the different positrons and electrons being accelerated by the magnetic fields of a pulsar there. But then there's also the third thing, which is, well, maybe we have some lack of understanding or something we've missed about those cosmic ray spallation and propagation in the Milky Way. And so the one thing you can do when you want to say, I want to talk more and think more deeply, is go measure something new about that spallation, that propagation of cosmic rays. And so we said that there's the secondary to primary ratio, right, which measures how much material cosmic rays have propagated through in the Milky Way, how many interactions they've undergone as they do this random walk through the Milky Way, right? And so the Chicago egg showed us this boron to carbon ratio for that. The kinds of spallation that you get, right, primary cosmic ray colliding, secondary cosmic ray out. Can we improve this understanding? Can we test this another way that's not related to positrons? And so the way that we're doing it now is through radioactive dating. Okay? So what I mean by that is you ask the question, how long have cosmic rays been contained or propagated, right, or undergoing interactions to produce secondaries? How long has that been happening in the Milky Way? What is the age of those cosmic ray propagations? And this is where beryllium enters again. Beryllium is useful because it's mostly secondary, produced from that spallation, and one of its isotopes, beryllium-10, is kind of like iron-60. It's this long-lived isotope. It decays with a half-life of 1.4 million years. And so the picture you can have is that you have these carbon primary cosmic rays that collide with the interstellar medium, producing radioactive beryllium-10. And if you go measure it, you're going to measure some fraction of beryllium-10 and some fraction of its stable partner that it decayed to, right? You're going to get beryllium-10 less if more decay is happening, if the age of cosmic rays is older. So if you go measure beryllium-10, if you measure very little, cosmic rays are very old, right? Because all of that beryllium-10 that was produced has decayed away. And this is a separate or orthogonal measurement to understand that propagation of cosmic rays in the Milky Way compared to the boron to carbon ratio. So the two that are usually, as in the past 20 years or 25 years or so, is beryllium-9, which is a stable isotope of beryllium, and beryllium-10. So beryllium-9 doesn't decay at all. Beryllium-10 does. And so if you go and measure it, and some instruments have in space, including that ACE instrument, as well as some balloon flights like ISOMAX here, have went and measured the beryllium-10 to 9 ratio. They've separated out, in the relativistic high-energy cosmic rays, they've separated out the exact nuclei and said, these are both charge 4. These are both beryllium, charge 4. And this one's got 5 neutrons. This one's got 6 neutrons, right? And if you plot that measurement of the ratio versus energy, you see a slight rise, but a lack of data out here. And that's actually where different models predict different things, depending on if cosmic rays are older or younger, or confined to what's called the halo of the cosmic ray propagation in the Milky Way. So if you have a larger region of cosmic ray propagation, then you're going to get a longer time scale for this propagation. You're going to get less beryllium. And the gamma ray measurements we have suggest that cosmic rays do indeed, because of these magnetic fields, propagate above and below the disk of the Milky Way, colliding with material there maybe, and then undergoing spallation there. So you have this propagation that happens at some scale everywhere in the Milky Way, but also above and below it. Now, the amount of material might be different above and below it. So this is a very hard problem to solve, right? That's why it's so important to measure the time scale of the propagation, to radioactively date it. And at lower energies of these cosmic ray secondaries, you expect more of the beryllium-10 to decay, so you expect less of it to appear here. And at higher energies, the reason it increases is because the cosmic rays are so fast, the beryllium-10 is so fast, that it's undergone time dilation. It can't decay. It's been traveling for so many millions of years, but in its rest frame, it's only been 1,000 years, right? Significant amount of it still lives. So this is what brings me to the instrument that I've spent 8 years of my life on, the high-energy light isotope experiment, or HELIX. A lot of sweat and blood went into this experiment, so you guys better pay attention. So this is a balloon-borne magnet spectrometer that's that's very similar to the heat instrument that separated out those positrons and electrons. It actually uses the exact same superconducting magnet that was flown in 1994. We took it, we refurbished it, and we flew it again on the HELIX instrument. It also utilizes the coincidence method. This is what we've talked about many times. We have, in our setup, we have a time of flight system that says, was the cosmic ray here? And then 2.3 meters away, it's very tall, it's like 12 feet tall or something. Yeah, 10 feet tall. 10 feet away, it's got this extra set of scintillator, bottom time of flight here. And that, if a cosmic ray hits both of those within a time window of basically some fraction of the speed of light, you get a measurement, right? You get a detection of cosmic rays. And we can measure the charge of the cosmic ray, we can measure its velocity, and we can measure its momentum. And this allows us to calculate the mass of the cosmic ray nuclei that went through our detector. So that's where you take the ratio of the momentum to the velocity. So this is a picture of what it looks like really before it flew. This was, I forget who took this, probably my colleague Heben, Dr. Zhang. She's now at Goddard, but I believe she was the lead on the solar panels for power systems. So you can see all of these different solar panels that give us power for our balloon flight. And then we also have an array of antennas above up here. That's for telemetry so that we can talk and listen and record some measurements. We can command the payload to change things if we want to. And this black object that's sort of hard to see right there is in the center is the magnet. This crane here holds the balloon payload up before the launch. And so we had our first flight 2 years ago from Esrange, Sweden in May of 2024. This is a picture taken just before the launch. We covered up all of our instruments on the side with this nice foam to keep it insulated so that it wouldn't get too cold. But you can see the balloon being inflated down here, attached to the payload, the HELIX payload here, just before launch. And so this is a picture from launch taken with our GoPro camera. So I love looking at it simply because I helped make sure it was taken. It's really cool to look at. Yeah, you should and ooh at that, right? But yeah, GoPro, pretty impressive, huh? So the kind of flight that we had, it was a 6-day flight. So you might not have seen a map of the world from this angle, right? But basically, if you look at the declination here, 50 degrees north, you can't even see Chicago, really, I don't think, right? And so this is where Norway and Sweden are, right? And you can see the launch point here, flying for 6 days, north of Iceland, over Greenland, and landing in northern Canada. It was a very interesting flight. Here's the PI, Professor Scott Wakely here at University of Chicago, looking at some of the data. And it was exhausting. The first day was fun. The last day was exhausting. It was such a fun time. Here's a picture of a couple of our colleagues goofing around because it was a good flight. So when it landed on Ellesmere Island in northern Canada. And that's the picture that was taken before figuring out what happens. Yeah, I know. 6 years, and then that's what happens to your hard work. And there's a picture of us recovering the data. That's Dennis from Ohio State University, grad student. Here's them taking apart the payload to ship it back via helicopter to repackage it for getting it back here to the University of Chicago. And there's the colleagues after the hard work's done, and it's back in a town instead of on top of a glacier. So we've been analyzing the data now and refurbishing because we want to fly again. That's the status of that. And so I want to take you through exactly how we're detecting these cosmic ray nuclei. So this is a 3D reconstruction of one of our cosmic ray events. You can see the time of flight. Yeah, I think this is right. So we have the time of flight system up here and down here. And so this I've talked about before is made of scintillator, right? So as a charged particle goes through scintillator, it emits light, and we collect that light to say there was a charged particle that went through. It's pretty large. I mean, these time of flight, these scintillator paddles are 1.6 meters across. We have a Cherenkov imaging detector actually below the magnet. So that's this rectangular structure here, trapezoidal structure here. Basically, the cosmic ray goes in, emits Cherenkov light, and then we basically, we almost like take a picture, an image of the Cherenkov emission. So I talked about Cherenkov emission in lecture 3 with neutrino tomography. So I'll just give you a brief reminder. If a cosmic ray, a charged particle, is traveling faster than light does in the medium of our material here, it produces Cherenkov light at an angle, and that angle is related to how fast that particle is going. And so that's what the animation is giving you a reminder of there. So we actually use that fact, right, to measure cosmic ray nuclei. We have the superconducting magnet here that bends the cosmic rays, and you can see, right, this is what was used on the heat payload to say positive and negative, but we do it now because we can say what the mass of that particle was, right, because if it has more mass, it's not going to bend as much. And this picture shows operation of the superconducting magnet, where I have my steel toe boot elevated from simply the magnetic field. It's not a trick. It was actually on for that photo. I should have taken a video because then it's more real. And then finally, through that magnetic field, we have to track the cosmic rays. And the way we do that with the tracker is we have high voltage that produces what's called a drift field. And so as the cosmic ray passes through a vessel of gas, that gas is ionized. So I've talked about charged particles going through material and producing ionization. So we actually use that fact to measure the ionization electrons that are knocked off from the cosmic ray traveling through the gas, and we measure that ionization here with our high voltage drift field to make a measurement of where the particle was at what time. So that tracks the particle through the magnet. So the tracker and magnet give us this momentum measurement, and I don't know what just happened to my pointer. And then the combination of time of flight and ring imaging Cherenkov detector give us the velocity and the charge. Okay, so we're still doing this ballooning thing, right? We're still saying, let's go measure these cosmic rays. These are a bunch of different balloons that are launched with all these different kinds of detectors from probably the 1940s or so, but we're actually still doing it. Our detectors are more sophisticated, we're more precise, right? We have the ability to go to space now and put cosmic ray detectors in space, but we're still doing the same kinds of ideas. We're trying to figure out still what's going on with cosmic rays, right? What's going on with cosmic rays? Because they can tell us what's happening in the Milky Way. We're really starting to figure out exactly how cosmic rays fit into the picture of the galaxy, of how galaxies form, of how different stars live and die, and how they contribute to the environment that we live in the solar system, right? And the things that are so interesting that are coming are what is the origin of those cosmic rays in the Milky Way and at ultra-high energies that I'll talk about in 2 weeks. But through the astroparticle lens, we can learn about the Milky Way and its high-energy sources. So thank you.